Oh man, switch to the main cam. Good morning slash afternoon, everybody. Hopefully everybody's doing good today. This is the ultimate learning position, says Khadija. The ultimate learning position. Lying flat on your back, staring at a screen, learning mathematics. The best, the best, the best. More like lay on your stomach. I can't do that. My back won't allow me to lay on my stomach. It has to be on my side or on my back. Like, lay on my stomach, then my back starts acting. I'm like, yeah, you're. Like, there you go. Classroom should replace desks as bed. I agree. Should be like the theater, you know? Theater went from like having these cramped, cramped seats to like the couches to like the recliners. Now they go to the couches. Now they go to like pretty much beds. Yeah, it just should be just like that natural progression. The issue is that everybody has a certain style of bed that they like, right? Whether it be like super floofy or super hard, could be a hard bed, it could be somewhere in between, It's like having steak, you gotta sleeping on a certain bed has its own. Everybody's got their own preference. Hey, Goldmash, how you doing? I hope you're doing well. Good to see you. How have you been? Watched a new Conjuring movie recently. It's so good. Oh, good. Glad you had a nice time. I don't watch too many horror movies myself, but yeah. I mean, I've heard the series has been pretty good. So I haven't watched many movies in general, to be perfectly honest. I really stopped watching movies quite a while ago since I don't even have television anymore. I mean, I'll go see a movie on occasion, but it's really rare now. I don't even have TV. I don't think it's too sad. I have different ways of like entertainment. So it's not like, oh, nothing happened to my TV. Nothing at all. My TV is sitting in my closet right now collecting dust, as it has been for the past 5 years. So I've locked myself out of the Discord account. Oh no. Yeah, you should request a new. See if you can request getting your password changed on your Discord account. I think there's a way you could do that, Goldmash. Say you forgot your password or something. You can have like a link sent to you and reset your password or something like that. So yeah. Yeah, I don't watch TV. I don't even have cable at all on my computer. So there's no point. Honestly, TV. There's not really much of a point to having television. I miss Flash games. Yeah, Flash is now outdated, and it's unfortunate. Flash is a good Flash was a good product for the time. I used to watch Flash animations back in the day, and to play Flash games on like Newgrounds and stuff. way back in the day. Now those days are gone past. Now that they have the 3D stuff and a whole bunch of other engines out there. But yeah, Flash games are like easy to pick up. Anybody could just quickly put one together and do it. So Miniclip, yep. I never went to Miniclip, but Newgrounds was my place. There you go. It's all gone. Yep, it's true. I know you probably tried to put a link in there. I think only mods and myself can put a link. So apologies about that. Oh, okay. I mean, hey, look, this math class can be like the new Club Penguin, okay? Maybe that's how we should do it. Only we learn math instead of just just trying to speed run the fastest way to get banned. Let me tell you the moderation. Day 2 trying to convince you to. Well, I'm glad we got right off on the right foot from the get-go. We're already at day 2. We're already doing fantastic. Absolutely fantastic. How can we distract you for 2 hours? Hey, let's Club Penguin this stuff, man. Oh my gosh. That's hilarious. That is absolutely hilarious. There we go. That should help you go mash. Josie, good morning / afternoon. Once again. I didn't say that. I gotta say that right now. It's important. It's a matter of decorum. Okay. I hope you're doing absolutely fantastic, Josie. Hopefully we're doing very well. You have a question on a certain problem in the book? Yeah, go for it. Ask me. Ask me. Absolutely, go ahead. If there's a particular problem you would like me to cover, then I will take a look at it and we can go over it together. Sure. I am here to help. Alright, x squared minus 6x minus 11. And you're trying to solve for x there, right? Does it give you a particular method they would like you to follow? Or can you use any method? Just depends. Some problems will give you any method. Some problems will say, hey, you should try this method. So I'm not sure if you want to do that one. You'll have to either do the quadratic formula or you do completing the square. Just depends which one you want. Which one, yes. Bursty, hello. How you doing, my man? Yeah, doing great. Welcome. Completing the square? All right, let's do it. Let's go to the big board. Let's go ahead and take a look how we did do that, okay? Some pre stuff here. So, all right. Let's write down the problem here first and foremost. Yeah, minus 11. Yeah. Okay. So the first thing we're going to do here, okay. Well, let's go through the steps here very carefully, and we'll see where we're getting hung up on, okay? So probably, hopefully what you did here first was add 11 here to both sides. All right, so you have x squared minus 6x is equal to 11. All right, let me turn that music down just a smidge. Here we go, half. Okay. Now, we're going to take this. We're going to take this minus 6 here. That's going to be our b. We'll take that minus 6. This is our next step here. We'll divide by 2, and then we're going to go ahead and square it. So here we're going to get negative 3. That's negative 6 divided by 2. Okay. And negative 3 quantity squared is going to be positive 9. So the question is, what do we do with that? So again, what we do with that here specifically is we go ahead and add 9 to both sides here. Balance it out just like so. All right, so you probably got up to here, no problem. Okay, now what we have to do next is we need to factor the left-hand side. Okay, that's what we need to do next. So we need to factor this left-hand side. Right-hand side is really easy. That's just 11 plus 9, which is 20. So that doesn't require too much effort to do. Now, factoring the left-hand side, again, it's whatever's in these parentheses here is what it'll factor to. So x plus whatever this number is. Hey, Jess. Good morning / afternoon to you. Hopefully you're doing fantastic. All right, so what we're going to have here is we're going to have x minus 3 quantity squared. Again, whatever is b over 2, that's what it's going to factor to. Again, no need to guess, no need to worry. Even if this is an ugly number, it would be x plus whatever number is in these set of parentheses after you divide by 2. It's that easy. Okay? Maybe that's what you're getting kind of hung up on, is like, how do you know what it factors to? Well, the fact of the matter is, the way we set this up with completing the square, you don't have to worry about how it factors because it always factors the same way. Yeah, so that you intentionally set it up this way so you have the predictable factoring so you don't have to guess. That's the important part there, Josie. Right. And then you can proceed to do the rest of the problem from there. So in this case here, just take the square root of both sides here, and what do we get here? We get x minus 3 is, let's finish this out. Square root of 20 is going to be 2 square root of 5, so that'll be plus or minus 2 root 5. So I'm just going to kind of, I know I'm skipping a couple things here, but just trying to get through this a little bit quicker. So we have 2 answers here for the price of 1, of course, as we always do. And so our final answer here is, our final answers, excuse me, going to be x is equal to 3 plus 2 root 5 and 3 minus 2 root 5 as well. And those will be our final results for that. Okay, well there we go. We have it easy peasy, lemon the squeezy. All right. Okay. That's because it's 4 and 5. 4 is a perfect square, so you said, yes, that is correct. How would I input the answer on the homework? Yeah, so there are buttons there. There are buttons that you can use for square roots and whatnot. So you would actually put it in exactly like, in this case, you'd be like 3 plus 2, use the square root key that they provide to you, that my math lab provides to you. So you have 3 plus 2 square root of 5, and then 3 minus 2 square root of 5. That's how you'd answer in that there. Yes, good morning to you and afternoon. I was just trying to answer the question first. I promise you. Nicholas, good morning / afternoon. Hopefully you're doing absolutely fantastic. Yeah, so if you want the square root of 20 again, square root of 4 times square root of 5. And then again, that's going to be 2 root 5. So, okay. Good morning, E-Man. Hopefully, there you go. Gave my graphing calculator to my sister last year, and I have no idea where it is. Neither does she. Oh boy. You need to tell your sister, like, stop borrowing my stuff and never returning it. Yeah. Yeah, that should happen. There you go. It's like, why are you borrowing my things and never returning it? Jeez, what's your problem, man? Did today's class start earlier? No, it is noontime. We're a little bit past noon here, but all problems solved exactly, right? Take it out on your siblings. Yeah. Yeah, ironic part about my calculator here is that my old calculator I gave to a friend, I told him to keep it for him passing his classes. Joseph, thank you for the follow. Appreciate you. Can you use the Demos website for graphing instead? You can. The only issue is that it won't be exactly the calculator, the TI 384. It'll emulate it, but maybe not exactly. So certain button presses may not be exactly the same necessarily, but yeah, you can probably get away with that without too much trouble, maybe. So just depends. Right, let's hydrate here. Got some Dunkin' Donuts coffee, so I'm gonna be hyped up on some caffeine for a little while. All right, so this is my calculator. This calculator I actually randomly found one day, and then nobody came to claim it. So I'm like, okay, I'll just keep it. So that was 8 years ago. So random calculator. Will you need a graphing calculator? Yes. Yes, you will need a graphing calculator. That is a requirement for the course, yes. Graphing calculator will make your life significantly easier. This is true. I'm pretty sure you get some cheap ones on Amazon, because 8384s are pretty much everywhere, so shouldn't be too much of a problem. All right. Let's get started here. Let's get going, ladies and gentlemen. We got work we got to do. Let's go to the main screen. Let's do some introductions and all right, let's do it. Okay, let's get started today. Welcome back, everybody, to Wednesday. All right, so today, ladies and gentlemen, last time, actually, let's talk about last time. We did section 1.5. That was a long section, I know. We're talking about quadratic equations, a lot of different ways we can solve quadratic equations. That took up pretty much all the time that we had last time. Okay, today we're going to be getting into chapter 2. Okay, so we're going to be doing 2 sections of chapter 2. This should go by much quicker than maybe last time. And we're going to be looking at a variety of topics here revolving around functions here. BMC, good to see you, Baba dude. Thank you. All right, so that is primarily what we're going to be focusing on here today. So let's go to the big board here. Let's talk about what functions are all about. We'll see how much we smell at functions. Yeah, let's find out how we can do things. All right, so let's go to the handout. Okay. All right, so let's look at question number 1 here for today's 2.1 example. Yay. All right, what is a function? Okay, so the formal definition of a function here is a relation between x and y in which one x value goes to exactly one y value. All right, so you've probably maybe you've seen this before where you kind of have two boxes here. You have two boxes. You have one is the X box and then not the Xbox 360 and not the Xbox One. That's the regular X box. All right, so and then here you have uh, you have the Y box here. All right, which is the next generation Xbox, and it'll be just as good. In any case, let's say you have a couple of places, couple of points here in X. Okay, we'll call it 1 and 2. We'll say 3 and 4 here. Again, at the end of the day, you could have 1 going to 3 and let's say 2 going to 4. Okay, so this is considered a function here, a relation between X and Y. I'm going to undo those arrows. Now, we could also have, say, 1 goes to 3 and 2 goes to 3. So they can all go to the same number. That's perfectly fine. Absolutely valid. This indeed is a function. What else actually counts here? Again, what actually counts here? You could just have 1, say, go to 4. And this also counts as a function. So you don't have to have like every number be represented necessarily, even though it's available. Um, However, one thing that is not allowed is this. So if 1 points to 3 and 1 points to 4, for example, this is an example of not a function. So this means, again, the key here is it goes to exactly one y value. So you can't go to, say, two y values. That is a big no-no. Okay, so that is que no bueno. We do not want that to happen here in this instance. All right, so so let's go ahead and take a look at an example here. Let's get a couple quick examples. This doesn't require too much. We'll just expand on this here. So let's say we had these points here that were in a set. Okay, so let's answer the question here. That this set of numbers here, these set of points here, is this a function? Yes or no? So is this a function? Yes or no? With these set of points, just simple yes or no. Is this a function? Yes or no? No, yes, no. Okay, so I have some answers here. Can two x's go to the same y? Yes, yes, that can. It went to two y's, did it? So 1 goes to 3, right? That's fine. Okay, so 1 goes to 3, so that's fine, right? 5 also goes to 3. That's okay. You can have everything. You can have this. This is perfectly acceptable. You can have 1 and 5 here, and let's say, for example, you have 3. Like this is possible. You can have this happen. This is just fine for a function. Again, if it goes to exactly one y value, that's all you care about. Okay? If it's the same y value, fine. Okay? That doesn't matter. All right? So the answer to this is actually yes. Okay? So 1 goes to 3, 5 goes to 3, perfectly valid, 100%. 3 goes to -2, that's its own separate dealio. Okay? So why I'm asking, making sure we clear up this definition here. Let's try another, though. Let's try another. I think maybe we just need to see another example. So it does back. How about this? How about these 3 points? Yes or no? Okay, so I got a bunch of no's. Okay. All right. So in this case here, the answer is indeed no. Okay, this is definitely not a function, right? Yeah, that's correct, Danny. So 2 goes to both -2 and -1. So we can't have that happen. All right? That's not possible. So I want to make note is like that's the fundamental difference here between what you see in the first example and the second example. All right? It's that little subtle difference, but it does mean the difference because based on the definition between yes, the first one's a function, but no, the second one is not a function as a result. Okay? So I just want to point that out here so that way you're clear about how functions from a definition standpoint work. Okay, now next part here as part of the definition here is the notation. Now I know a lot of you or all of you have seen this notation before. This is the most common notation here, which is f of x. Literally, you can swap these letters around. You could say g of x. You can say h of y. If you put the function in terms of y, that's perfectly fine. Okay, so you see a lot of different ways to kind of define a notation here, f of x being the most common. So again, we could say f of x is equal to 3x minus 2, a very classic example. And as is noted here, f of x is the same thing as y. All right, so I mentioned that this was asked yesterday, and Yes, this is definitely true. So get into the mindset here is that f of x being 3x minus 2 and y equals being 3x minus 2 are the same exact thing. There's no difference between both of these things. Again, it's just written differently, but in reality, they're exactly the same. So that makes your life very happy. Okay, so you don't have to try very hard to be like, okay, yeah, good beans and rice. Yes, good stuff. All right. Um, I think that's pretty easy, pretty simple. All right. Questions so far? Any questions? Any questions so far? Hopefully everybody is on the same wavelength here, so we're good. Good. Okay. All good. All right. No, right. Excelente. All right. Okay, so let's focus on number 2. All right, so that's the next thing on our agenda here. Numero dos. All right. So number two says, how do we evaluate functions? Now, this is the important note. We talked about this before, probably on the first day of class. But again, anything we always put parentheses around what you substitute. That's going to be the key around doing anything when it comes to evaluating functions. All right, so for example here, let's make up a function. Let's see how we can work with it. So let's say f of x here is equal to, um, let's say the square root of x minus 1. Okay, so if let's say that's what we have here, okay, the square root of x minus 1. And let's say, for example, we wanted to evaluate f of 10. All right, so this is what we want to do. We want to evaluate f of 10. Now, the only thing that we have to do is put 10, we substitute 10 in for every x in f of x. That's all we're doing. So if you can imagine here, you're taking 10, and all you're doing is, let's put it here. That looks terrible. Let's try that again. So we're going to put 10, we're going to put it into this x right here. Okay, that's all we're going to do, because this 10 is in for this x, so it goes into that respective x. And again, if we do it out, that's going to be 10 in parentheses minus 1. Again, that's going to be the square root of 9, which is 3. Okay, so here we get 3 for our answer here in this problem here. And that's it. Simple enough. All right, so there we go. Easy peasy lemon squeezy. All right, so it doesn't require too much effort, in all honesty, but again, that's all we need to do. Let's try another one here. Take a look here at a couple others. Yeah, there's one I want to look at in particular that actually bears some importance here. So, okay. So there's a few examples here that I want to look at because it does make things a little bit more clear for things that we'll look at later on. All right, so g of x is equal to x squared minus 10x minus 3. All right, so here's a random function. All right. So let's say we're doing let's look at a couple of these here. Let's do g of minus 1. All right, so let's do that first. Okay, so can anybody tell me here, we plug in minus 1, what's going to be our result here? What's our final answer for this? Because we got g of minus 1. What do we get? I know people will come up with one of two answers. So g of minus 1, what do you get here for your final result? What do you think? G of minus 1. Let's see a few, see, okay. All right, not sure, but we said eighth, okay. Okay. All right. We got 8 or 6. All right. Got 8. Okay. Let's go ahead and take a look here and see which one of those two answers is correct. Some people like 8. Is it 6? I'm not sure. I said okay. Now, the reason why I do this example, there's a big reason why I put this note here. All right. If you don't, if you're having trouble with this one here, it does matter. Look, the fundamental for this will be very helpful for what we're going for a lot of topics we'll do later on. So we do this repetitively over and over and over again. This is especially true with negative numbers because signs could easily change. Reason why we put parentheses is exactly this point. So what happens here in this case is that for -1, again, because signs can easily change, we put parentheses here, we're going to have -1 quantity squared minus 10 times -1 in parentheses minus 3. Now here's the reason why you either get 6 or you're not completely sure. The reason why is because I feel, maybe I'm going to take a wild guess, a very educated wild guess here. And this will require me to show this off here on the calculator. Is that you're gonna use the calculator? You'd be like, you know what? I'm not sure, and you're like, okay, so I bet this is what happened. So I'll be like, okay, you do this, like -1 squared, and then you're like, all right, minus 10 times -1, and then minus 3, and then you got 6. This is what you probably did, or you're probably saying this is what probably happened. Well, here's the issue. This is what happens when you don't put parentheses. This is what happens when you do put parentheses. Let's see what happens. Let's showcase why parentheses are important. Oh, magically we get 8. Look at that. We get 8. Don't take it for granted. All right? Parentheses are incredibly important because -1 with parentheses quantity squared is +1, not -1. If you put it without parentheses, it's going to be -1 instead of +1, which it should be. The rest of this is easy. It's like -10 times -1, that's +10, and you get -3 here. So you get 11 minus 3, which is 8. So again, simple premise. Okay, simple premise. So why did you put x? So why did you put x if you already substituted x with -1? Um, what do you mean by that, Light? I'm a little confused. I mean, that's the question here. The question is that this is -1 here. On the calculator? Are you talking about times -1 here? This is just the times key here. That's all. Yeah, so this is times -1. So -1 squared minus 10 times -1. Oh, okay. Yeah, this is the times key here. Yeah, that's the time symbol there. Yeah, so the square is only being applied to the 1 and not the whole thing. Correct. That's why the parentheses are important. Okay? Because that's how the calculator interprets it. It'll interpret, without the parentheses, it's going to interpret the negative and the 1 as two separate things. And it'll do the exponents first as part of order operations and then apply the negative. However, with the parentheses, it'll say it's -1 times -1, which should be +1 at the end of the day. All right, so you're telling it what to do, only it's telling it only you're telling it what to do, only because you skipped a step, it's doing what you told it to do. As my old computer science teacher told me, is that computers are dumb. That they'll do exactly what you want them to do. So, I thought about it. I'm like, he's right, actually. Most of it's human error. Like, yeah, it's because we tell it what to do. It does what it wants to do. It does what we tell it to do, and it may not do what we actually intended it for it to do. So, yeah, I want to be sure that you guys are clear about why this happens in this case. So if you're relying so much on the calculator, maybe not. I don't always. Sometimes it's good to use a calculator, and sometimes it's not great to use a calculator because of that over reliance. So that's why I want to be sure that these fundamentals are put in place So you're not guessing and you're not relying on something here. You can physically see it for yourself. You can figure it out for yourself as much as the calculator can. Okay, so over reliance on one thing is not great because if you go back to the crutch one too many times, then the issue is that you're not thinking for yourself. So you want to avoid that at all costs when it comes to a subject like mathematics. So um, you don't want to, like I said, the moment you put yourself in the guessing format, then it's like, it gets to be a little bit tough. All right, let's try another example here. All right, that one there. All right, now, next we have g of x plus 2. All right, so we have g of x plus 2. So what I'm going to ask you now is, okay, what should this function look like if I have g of x plus 2? So before we, don't tell me what the final answer is. It'll take you some time to get this final answer. We'll go through that together here. But what I want to know is, what should g of x plus 2 look like here if we plug in, we take x plus 2? What does that look like here when we plug that into this function? And you type that out in the chat there. So, what do you guys think? G of x plus 2. Okay, so what would that look like, Josie? In your, I want to know kind of from your perspective here, what would that mean to you? How would you write out your first step there if you're trying to figure that out? Okay. All right. Very good. These answers here are correct. Very good. All right. So now we have a good fundamental understanding about how this works. Even with x plus 2 put in there, okay, what's important to note is that all we're doing, again, just to reiterate here, we're just taking this x plus 2 and we're putting it in for every x in g of x. That's all we're doing. Okay, no fancy tricks, no nothing. All right, so the answers here that I see in chat are correct. We get x plus 2 squared minus 10 times x plus 2. Okay, and then the minus 3 here at the end. That's right. All right, so this is what we're going to do before we do anything else. Okay, so just pointing that out there, be like, hey, we're approaching it the same way as if it was a number. There's no difference in how we're going to do it. So again, one of the biggest causes of confusion in this problem here is that people think, oh, we'll just tack on 2 at the end. We'll just plus 2 at the end. And the answer to that is no. You're replacing every x with the expression here of x plus 2. That's how we actually figure that out here. Okay. Let me ask you another question here. Let's answer another question here. What is what is x plus 2 squared? What's that equal to? What's x plus 2 squared equal to? What's that equal to again? X plus 2 squared? Is x squared plus 4? X squared plus 4 there, okay. So I see x squared plus 2x plus 4, x squared plus 4x plus 4. Oh, this question is so good. All right. All right. Whoa, ho, ho. All righty. There's a reason why I asked this question here. Because again, this is all about fundamentals 101. Now, Josie asked the question here, would you have to FOIL? The answer is yes. All right, absolutely 100% true. All right, so good on picking up on that, Josie. So the answer here, let's talk about this here. All right, so a lot of people said x squared plus 4. Now remember, x squared plus 4, that answer in particular, let's talk about x squared plus 4. X squared plus 4 is the trap answer. Okay, that is the trap answer. That is the answer that will mark that wrong. Okay, so x squared plus 4 is the trap answer. That is what you don't want to put down here. Let's talk about this here for just a moment. Okay, so this is something to kind of remind yourself of here once again. All right, so again, we do have to FOIL out here. So again, x squared, x plus 2 squared here, and we'll do this workout here. We have x plus 2 times x plus 2, right? That's what we have here in this instance. All right, so again, we do need to, as Josie stated here, we do need to FOIL here appropriately. So we take x times x times 2. So that'll be x squared plus 2x. Then we have to take this 2, multiply by x, multiply by 2. That'll be 2x and 4 here. Okay. So in fact, we get x squared plus 4x plus 4. So those of you who wrote that down, and I saw a few of you did, absolutely. That is the correct answer for x plus 2 quantity squared. Okay, so make sure we don't fall for those traps. Okay, so let's put a note here in this case. I think a note is very appropriate here for this particular part. All right, as a fair warning for everyone. So that way we make sure we don't fall underneath these traps here. And this is one of those math traps. So a warning here. All right. Do not forget the middle term. Okay. All right. So that's a fair warning here. Again, I like this question a lot because of this fact here. Not only does it go over the fundamentals here, but again, reminding ourselves of one of those things that we tend to slip up on throughout the course of the semester if we don't nip it in the bud now. So just be sure not to forget about that. If you didn't get it right, that's fine. That's exactly what we're here to do in these sections is just, again, shaking out those cobwebs, making sure that we get our bases covered here when we do more advanced examples. Make sure we got ourselves patted down, no problem. So if we rewrote this here, we in fact have x squared plus 4x plus 4. And then we distribute this minus 10 here to both of those terms. That'll be minus 10x. Minus 10 times 2 is minus 20. And minus 3. We'll add up the like terms here. We have x squared. What do we have here? 4x minus 10x minus 6x. And we have 4 minus 20, that's minus 16. Minus 3 is minus 19. So our answer here, a final answer here, if we add up all the like terms and once we put it all together, be x squared minus 6x minus 19. And there we go. Got it. All right. Any questions about that? GG indeed. Thanks for the posture check, Blink. Hydrate, sure. It's like this particular topic. Like I said, it looks easy. It's like, well, it's those small little details that trip up a lot of people. Heck, it's even tripped up me when I was learning this stuff. That's what tripped me up the most. Is like, yeah, I can't really forget that I'm doing it the same way. I can't really forget about how to square stuff out. So if it helps, again, just write it out so you don't forget that middle term. Then trust me, it'll make it easier. Why isn't the last number negative 23? Because we had the plus 4 here. That's why. from the x plus 2 squared. We had this plus 4 out here. So you had 4 minus 20 minus 3. So you just don't forget that extra plus 4 that we had here from this x plus 2 squared. Yes. Yeah, so just adding up the like terms there. Oh, no problem. It's okay. Just go through each piece carefully so you find its respective friends that you can hopefully combine and put together. So that's what we're after here. Nothing too crazy, I promise. Nothing too crazy. Makes more sense? Good. That's exactly what we're after. Exactly what we're after. Question mark. Yeah, that's right. My job, I remember that. All right. Let's take a good look here at the next set of questions, okay? All right, so let's look at number 3 and number 4 here. All right, so number 3 here, number 4 talks about domain and range. So it says, what is domain? So domain here is all x values that work, meaning to say, if I take an x value into a function, okay, I plug it in, and I get some random y value out. Again, I don't care what the y value is, but if I get an answer, that's great. Then I know that that number there is part of the domain of my function. Easy enough. Plop it in, it gets an answer, you're in. Great. All right. Now, the biggest issue about finding domain of a function here is basically there could be a lot of choices about what the domain of a function could be. Again, you have an infinite amount of values. So the method to typically find the domain is to find all the x values that don't work and exclude them. So sometimes it just depends on the property that you're given here that could determine the actual domain of a particular function. All right. So here we have, let me see if I have that down there. Yeah, all right. I'm going to answer one question down there as well, so I'll do that in just. Um, we also have range here. Range is all the possible y values that you can have in a function. Again, just whatever answers that you do get, now you actually care. And you're like, okay, well, what's the minimum y value I get? What's the maximum y value I get? I said that seems fair. Okay, so how is this going to work here? Let's put up a function here. Let's talk about it. All right. Um, and yeah, I think that's fine. All right, so let's look at let's look at a classic one here. Let's look at the square root of x minus 1, a very classic example. Okay, let's say I wanted to find the domain and the range of this particular function. Okay, so there's several ways you can attack this particular problem here, but there is a good tried and true method here is just to understand what you have here. Here we have a square root, right? This is what we have. We have a square root of x minus 1. Now, we have an infinite amount of values of which to choose from, okay? That part is definitely true, okay? But let's follow the logic here for just a second. What do we know about square roots? Okay, let's think about it this way. What can we not take the square root of? What's a restriction on a square root? What can we not take a square root of, right? Let's think about it that way. A negative, right? Because we talked about it previously yesterday, right? We said we take the square root of a negative number, we get I, right? We get like some form of I. But we don't get nice numbers when we take the square root of a negative number. So that's correct, okay? Very good. So in this case here, because we can't take the square root of a negative number, what has to be true is that x minus 1 here has to be bigger than or equal to 0. All right? So x minus 1 has to be either 0 or above. It has to be 0 or positive, okay? If in order for it to work and be part of my domain, this absolutely has to be true, 100%, okay? So we solve for this inequality here. Add by 1 to both sides. I say that's fair. Okay, and so here we get x is bigger than or equal to 1. Okay, now, however, this particular guy here is going to be expressed a little bit differently. Now, what may be required here for like my math lab is they may not want to accept this as a potential answer. Okay, x is bigger than or equal to 1 is definitely the domain of this function. There's no question about it. But what they may ask you to do is put this in interval notation instead. So go down to question number 7 here for just a moment. And they would like you to go ahead and express this answer here in terms of interval notation. So we're going to cover interval notation here using this example as a backdrop. So again, what is interval notation here? Remember that interval notation here deals with parentheses and brackets, okay? So we have parentheses here, means it's not included. Brackets here means is included. So parentheses meaning not included, meaning strictly less than or strictly bigger than. Brackets here mean being included will be less than or equal to or bigger than or equal to. Go ahead and make this. Okay. Now, there are an associated amount of rules here. Again, it always goes low, comma, high. That's always true. Ignore the parentheses there, but again, it always goes low, comma, high. And for infinity and minus infinity, we always put a parenthesis next to infinity or minus infinity. That's a rule here. Also, if we have solid circles or open circles, solid circle means a bracket, open circle means a parenthesis. So if we run into that situation, then you know that we're dealing with those two guys. Okay. In any case, let's take a look at the inequality here of x is bigger than or equal to 1. Okay, since that is the domain of our function here. How can I write in interval notation? How can I write x is bigger than or equal to 1 in interval notation? How can I write that in interval notation? How can I write x is bigger than or equal to 1 in interval notation? How can that happen here? How can I write x is bigger than or equal to 1 in interval notation? What's our low value here if we talk about x is bigger than or equal to 1? What's our low value here? We have 1 and infinity. Okay, so we have 1 to infinity, that's true. 1's our low value, infinity is our high value. Oh yeah, no, I got you. Right, 1. So we have 1 comma infinity, right? Because again, it goes up all the way up to infinity, right? It never stops. It's any number bigger than 1, it's fine. Now for infinity, right, we follow the rule here. If we have infinity, we put a parenthesis next to it, right? How about the 1? Do we put a bracket or do we put a parenthesis next to it? Yeah, what tells us that it's a bracket? I agree it's a bracket, but what tells us that? How do I know this is a bracket again? I agree it's a bracket, but how do I know? Greater? Greater or? How do I know it's included? Greater than or equal to, okay, good. So you have to look at the inequality here. The inequality here says greater than or equal to, right? So take a look here, which means it's included. So again, if it says greater than or equal to, so that's why I put this here. If you see these two symbols, one of these two symbols, less than or equal to or greater than or equal to, then you're going to put a bracket next to that number. Okay? That's going to be the dead giveaway here if we're going to put it in proper interval notation. All right? So hence why we put a bracket here next to 1, because we have greater than or equal to 1. If it was like strictly bigger than 1, then I'd have a parenthesis. But here it's bigger than or equal to, we'll have a bracket next to that 1. Okay? Are there any questions about that before I move forward? Want to be sure that any questions about anything so far, by the way? No. Don't get this confused here. No, 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 no. You do not put a bracket next to the low number always. No. Okay? You put a bracket next to the number that is either greater than or equal to or less than or equal to. So it's the same thing as if I did. Let me show you how this works. Let me show you another example here. If I had this, for example, right? Let's say I have this, okay? So x is bigger than 1, less than or equal to 3. The way I put this in a notation is I would put a parenthesis next to 1 because it's strictly bigger than or strictly less than. Okay? However, for 3, this is less than or equal to. Hey, monkey, how we doing, my dude? Good to see you, my dude. Thanks for coming by. Hey, you're welcome in the stream anytime, monkey. How was partying stream yesterday? Hopefully it was good. Is there a rule at some point you need to flip the inequality symbol? Only if we divide or multiply by negative numbers. Fritz. No, 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 man. No, dude. Monkey, you don't have to worry about it, man. Feel free to stop in, interrupt me. It's all good. Yeah. Yeah, so here we have strictly bigger than 1, right? So 1 has the parenthesis and 3 has the bracket next to it, okay? So you can see here again. That's how we can. That's why it's not always I say oh the low number always gets this guy and then the high number always gets this guy. No, we have to look at it from a case by case basis. So we have to determine it based on the inequalities that we have here in order to make that determination. Okay, so I don't want to be telling you, oh yeah, you gotta it has to be this way, only no, strictly a case by case basis, and then use the rules appropriately here to write that down. For part of how we would graph functions, I think okay. Yeah, we're gonna come back to that question there, Joseph. We haven't quite gotten there yet, so I just kind of skipped ahead a little bit. So how do we write the range? Yeah, so the range will be written in the same notation. All right, so if we want to find the range here is going to be different, of course. Again, for a square root function, this is always going to be applicable. If you want to see this in action, let's take a look at the graph here. You can see the graph here. That's really not too hard to do. So we'll put the square root of x minus 1 here in the thing. Would you ever use brackets for both? Yeah, you could use brackets for both. If this was instead, let's say that we had, let's say we had this. Here's where you could use brackets for both. If we have bigger than or equal to, less than or equal to, then indeed you would have 1 comma 3. So this would be a range from 1 to 3 with 1 and 3 included. If blink. So that's we could use 2 brackets again, strictly by a case basis based on the inequalities that we got. Okay, so that's why we're going to have general rules and then just apply those rules there. Let's take a look at the graph here for this graph. That graph looks awful because that isn't the graph I wanted. That wasn't the one I wanted. Let's go to the standard. Here we go. That's better. All right. um, all right. So let's take a look here at the range. The range is all the possible y values. All the possible y values. So all the possible y values here, again, we're going to look at y here. For square root functions, it's pretty easy. Again, in this case, as you can see, in this particular instance, it's always going to be, from 0, it looks like 0 up to infinity. So it looks like 0 is included here in this instance, being a basic graph here. You have 0, comma, infinity with a bracket next to 0. And infinity always going to get the parenthesis treatment next to it. So 0 comma infinity is how things will work out here at the end of the day for this dude. Okay. Again, you can look at the graph here if you want to look at the y values there. That's one way to look at it. Or again, if you understand some of the properties of some of the functions that you're looking at, that's another way to look at it. It just kind of depends which way you want to do that. So, are there any questions, by the way? Any questions? Holy jeez! Moral Monkey gifting 5 tier 1 subs? Jeez, holy smokes, dude. Dude, you don't have to give subs. I don't even ask for subs on this channel. Holy cow, man. Thank you. Thank you so much. That's really super kind. Wow. Dude, dude, I don't know what to say about that. That's love you, Gypsy. Thanks. Thanks, Monkey. Love you too, buddy. You take care of yourself. Holy smokes. Wow. Thank you so much. That's really super kind of you. Wow. Well, that was unexpected. There you go. 5 gifted subs. Jeez. Holy moly. Like I said, I don't ask for subs or donations. I love doing this job. But man, holy cow. I love this community. This community is so great here on Twitch. It's such a great community. You guys do me so proud. I can't really say anything more than that. Oh man. Thank you so much, Monkey. I really appreciate that. That's really super kind. I hope to see you on Parting Stream, by the way. So if you're still here, hopefully you'll see you on Parting Stream. Get to hopefully get a chance to chat a little bit more. All right. After that, holy moly, holy cow! Thank you so much. Um, yeah, where was I? Train of thought. Oh yes. Okay. So as I mentioned here, it does depend on the function that you have here and the properties of that function here. So a square root function, of course, is going to act differently than that of an x squared function or whatnot. It just depends on what you have here for your function and their properties associated with that. Let's do one more here. I think one more is fine here. So one more function here. That even no, that's just not a polynomial. What am I thinking? We're not talking polynomials yet. Let's do this. Okay, 1 over x minus 2. 1 over x minus 2. Okay, let's think of the domain here of this function. Well, in this case here, we're dividing, right? So if we're dividing here, if we're dividing here, what happens here in this case? If what doesn't work if we divide by anything? What can we not divide by? Let's answer that question. Get the bottom to the top. Well, that's not what we're doing here in this case, Joseph. We're just answering the question here. What can we not divide by? Because what we're answering here is we're trying to figure out what can we exclude here from this function, right? What numbers can we exclude? So we're just going to take a look here at we're just taking a look here at the property of just a rational function here in this case. So in this case here, I cannot divide by 0, right? That's a big no-go, right? I'm not allowed to divide by 0. So that's kind of the thing that that's the question I'm really want to answer here. Is I'm looking at the property of that function here. You know, is there something that's going to make that not doable if you kind of want to put it that way? So in this case here, x minus 2 can't be 0. I said that's fair. So what makes x minus 2 equal to 0? Let's find what out that is. And that's pretty easy. So that's going to be 2, right? Right. So the thing is that x cannot be equal to 2, okay? That's the only number that makes this bad. All right? Any other number, we're going to get whatever answer, and that's going to be fine for us, okay? We're not going to be in bad shape, okay? We're going to be in good shape here. All right? So x not equaling 2 is the only one that we want to exclude here. So the question is, how do we go ahead and exclude 2 and keep everything else? Okay, Now, maybe you're going to have a tough time with this. Maybe you're like looking at this and you're like, well, it's not the same inequality that we talked about here last time. I said, okay, you know what? That's fair. All right, absolutely 100% fair. So, what's another way? What's another technique that you can actually, um, take a look at the domain here and look at it from a interval notation perspective? So, another way to kind of focus on this is here's another trick that you can use. Another trick you can use here is to just draw out a number line. And you're probably saying, "Wow, drawing a number line seems kind of silly." And be like, "Yeah, that requires more work." But in actuality, for some people, when I've done this many times, but for some people, this actually turns out to be a lot better because a lot of people are very visual, and sometimes you just need that visual representation, right? If you say x is not equal to 2 or whatever, okay? You know what? That's fair. I ain't gonna lie. That's absolutely fair. So, okay. So here's the way I would do this. All right, so in this instance, let's draw out a number line. Here's a number line, just a very generic number line. So here on the left, we have negative infinity. Here on the right, we have positive infinity. I said, fine, it is what it is. And then somewhere in the middle here, we have 2. Now, next to negative infinity and positive infinity, we have parentheses. So parentheses are going to be out here. I said, fine, it is what it is, right? So um, x is bigger than 2 because it can't be 2 and it can't be less than 2. Well, that's not true here. That's why I'm going to draw out the number line here so you can physically see what happens here in this case, right? So we have a parenthesis here, we have a parenthesis here for a negative and positive infinity, right? So if x cannot be 2, right? X can't be 2, we've established that. What would we put next to 2? Would we put a bracket or would we put a parenthesis here? Because part of that answer is kind of correct there, Jess. Part of that answer is kind of correct. I won't lie. It's not completely correct, but it's kind of correct. So what would I put next to 2 here? Would I put a bracket or would I put a parenthesis? Okay. Right. All of you have the same exact right idea. Right? Okay, very good. This is correct. Actually, each one of these answers here is correct. 100%. All right. So we have a parenthesis here on negative infinity. Actually, you know what? I'm going to do it this. I'm gonna put, trying to debate with myself and be like, how am I going to express this out? Okay, so parenthesis here. Now at 2, we're going to put parentheses here. We're going to have a parenthesis here, and we'll have a parenthesis right here. And as you see here, we've excluded 2 and kept everything else. All right. Last side round other. Well, actually, actually, you're talking about another concept there, but it doesn't touch 2. That's true. So it gets really darn close. We want to include every number that isn't 2, essentially. But mixing a couple. No, no, no. That's fine. That's fine. There's a couple things that we'll talk about here later in the semester here that'll relate to what you just said here. But we're not quite there just yet. Um, um, in any case, uh, here are the two. Here, as you can see, are the two intervals that we're going to have to express x is not equal to 2. So here we have negative infinity, comma 2. And then if you want to combine two intervals together to express a domain, we put this big old letter U. It's like a big old letter U that stands for union. Um, this is a formality here. And we have 2 comma infinity with some parentheses. Notice the notation I used directly on the number line. There you go. Simple enough. Okay. Seems fair. Same thing I would do in the last problem. The last problem, if you wanted to do a number line here with the last problem, it would be the same way, right? You have negative infinity, positive infinity. You want x is bigger than or equal to 1, put 1 here. Put a bracket there, put a parenthesis there, and there you go. You just put it together, bada bing, bada boom, you got a winner. Hey, hey. All right. Any questions about that so far? Hopefully that made that a bit easier to kind of understand here. Um, if you want to know the range for this particular function here, the range here is everything. So except for 0. So why would you ever want to include? I don't know. I forgot you can you things. Yes. You don't want to include two. Why would you like for any reason? I don't know. I don't know. Not in this function anyway. You don't want to do that here. The range here actually a little bit different. You can't have 0 here actually for the range. The range here would be negative infinity to 0, and you want to exclude 0 and 0 to infinity. That's the range here for this function. So got that there. Good to go. Easy peasy lemon squeezy. All right. Okay. So smelly. Eventually, stuff will happen. Don't st All right. Okay. All right. Easy enough. Okay. So let's move on here. Got a few more things to do. There it is. Okay. Let's talk about graphing functions here. How do we graph functions here? As was asked earlier here, now I'll go ahead and acknowledge this here. It's the same as we graph equations. All right, so there's not going to be any difference here about how we graph functions compared to equations. And the reason is because if we go back to our little note here, our little note is that f of x is the same thing as y. So the way we graphed equations here from before is no different. So again, if you see, for example here, let's do a quick one here. Um, Let's do f of x here is equal to, let's try x squared minus 2. Okay, in this case here, I want you to approach it the same way we did last time, which is just make a simple XY chart. Okay, so this is why I want to kind of streamline this process here for doing it by hand here, because I don't want it to be like super overwhelming. We know an XY chart, and you know that Y is the same thing as f of x. So rather than make things confusing, I said, well, why don't we do it the same way we did, previously, without having to do all the guesswork. So again, you could pick values for x. 0, we get -2. 1, we get -1. Pick -1, we also get -1, and so on and so forth. And you can still just do the same thing here. Plot your points, connect the dots, da 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 da, and then there you go. You got yourself a winner. It really doesn't require too much effort here. It's pretty much exactly the same thing that we had discussed from before. So I just wanted to point that out here is that the methodology here to actually do this out is no different than what you've been doing before. It's exactly the same. So in that instance, it's like, okay, hey, that's all right. Are there any questions about graphing here, at least in this instance? Is that uh, yeah, it's like I said, I don't want to be like repeat the same thing. It's just again, remember a function's just a reskin of an equation. So it's like y is equal to whatever. So any questions about that? Questions? Cool. All right. There. All right. Next, let's take a look here at more things. How do we know a graph is a function? Okay, so that's the next thing we wanna focus on here. How do we know a graph is a function? Well, what we do is we do what's called the vertical line test. This was mentioned earlier here. But with the vertical line test. So the way the vertical line test works is that we draw a vertical line anywhere on the graph. If that vertical line hits 2 or more points on the graph, then the graph is not a function. This is because of the definition here that we have for a function where it says, well, one x value can't go to 2 y values. If you draw a vertical line and hit 2 or more points, then that's exactly what it represents. It'd say one x value goes to like 2 y values, and that would be bad. We don't want that to happen. So that's what the vertical line test here represents. So let's take a look at a few examples here. Simple yeses and nos will suffice. It's just like, just kind of easy easy to see here. So let's look at some examples here for this guy. How about this? Is this a function? Just this line here. Is this a function? Yes or no? All right. Cool, cool. Yeah. I agree. The answer is definitely yes. Okay, draw a vertical line. We're only hitting 1 point. Easy. All right, how about let's try another one. How about this? How about this? All right, 100%. Agreed with everybody here. No. All right, let's look at another one. How about this? All right, this one here is a yes, definitely true. We only hit 1 point here. Let's try one more here. Yeah, let's try that last one there. About this? Agreed. The answer is no. Good. All right, a vertical line is just going to infinitely hit all the points. And wow, that's a perfect vertical line. Never thought I'd do that. Um, all right, easy peasy lemon squeezy. All right, good beans. Okay, questions about that. All right, let's move forward then. Let's do other things. All right. Okay, now we're gonna get right into section 2.2. Okay, so let's talk about that here. And let me prepare to absolutely wow you with my astounding master's degree skills of mathematics. Okay, tell you what master's degree skills in mathematics is going to get you. Let's look at question number 1. What are increasing, decreasing, and constant functions? Increasing is a graph that goes up. There's a formal definition, but let's just focus on the easy part. Increasing, it goes up. Oh man, never expected that to happen. Increasing, it goes up. That's pretty great. That's pretty great. Decreasing, it goes down. Unbelievable. Let me tell you, it's the hardest thing. Um, it's math, pretty complicated. Okay, decreasing, it goes down. Okay, graph that goes down. There you go. Constant. Basically a graph that's perfectly flat. It's just like, yeah, there you go. Bam. You got a constant function. I know you didn't see that coming, but you know what? There you go. That's how you answer question number 1. It's just I know it's tough for I know it can be a tough concept, but I promise you get through this no problem. Okay. Hard. It's very hard. Good job, we did it. Now now the question is why is this important? Okay. Let's talk about why the heck are we talking about why the heck are we talking about increasing, decreasing, and constant? Can a constant function be vertical and horizontal? And horizontal. It gotta be so. Just horizontal would be correct, sir. Just horizontal. A vertical is a little bit different because it has a unique property to it. Because there is undefined slope for a vertical line. We'll talk more about that once we reach there. I think it's later on in this chapter, honestly, but um, yeah, it's just horizontal for that, Danny. Good question though. That's a fair question. Um, yeah, vertical is just kind of its own little thing. So All right, but let's talk about how we're going to actually apply this here in this case. Let's look at question 2. Question 2 says, what are relative maxima and relative minima? Now, this is not going to be the only time we're going to talk about relative max and min, but let's talk about what the base definitions are at the very least. So, a relative maxima is a point that is the highest point within an interval on the graph. So, i.e., a top of a hill sort of scenario. Basically, if somewhere in the graph it increases to decreases, then we're going to get a relative maximum. So what exactly does that look like here? Let's take a look at that. So relative max, let's say we have a graph that looks like this. Okay. Let's say the graph looks like this. Now, this here at the very top of this hill is going to be the relative max. Again, there is a difference here. Relative max, again, is the top of this hill. Notice you increase as you're going up to this very top, and then you decrease right after you hit that point. Okay? It's not the absolute maximum. All right? Absolute maximum would be like the very top of the very top here, but the absolute max would be like infinity. Absolute minimum would be like minus infinity, but that's not what we're talking about here. We're talking about relative maximum and relative minimum. Hence why I use top of a hill as opposed to like the highest point on the graph. So um, it's a little bit easier to kind of understand it in that frame. A relative minimum is just the opposite here. So a relative minimum here is going to be the point that is the lowest point within an interval on the graph. So we go from decrease to increase, i.e., say a bottom of a bowl. So again, this orange point here would be a relative minimum. All right. So if we there could be now again, I do want to point out one thing here, and I guess I should put this as a side note here. So let's put this as a note here as well. So one note that I do want to point out here about relative maximum and relative minimum is there can be multiple relative max and minimum. So it's certainly possible based on a lot of graphs that we may look at here in this class, we could find like 2 relative minimums and maybe 3 relative maximums. However that curve is going to work out. That's just the way it works out. Okay, so it's not just limited to one. You could find several. Okay, so you don't have to worry about that too much. All right. Okay. Any questions about that so far? Okay. Now I do need to actually that up. So let me go ahead and grab that here for just a moment. Just a second, folks. Need to grab something from eText here. Specifically, something in the eText that I should show you. Um, uh, okay. So what I'm going to have put up here on the screen is I'm going to go ahead and we're going to do a couple of these examples here together. Okay, so this is from the eText here. So I'm going to make it a bit bigger here so it's a bit easier to see for everyone. I don't have the best eyes myself, so sit here and tell you, yeah, you should be able to see everything. Like, yeah. So. All right. In any case, let's do some problems here talking about constant. Let's talk about increasing, decreasing, constant, and relative max and min. Okay. So let's take a look here at number. Which one do I want to look at here? Sure. Okay. So let's take a look here at number 2. Okay, so we take a look at this parabola here. All right, can anybody tell me here what would be the intervals on which the function is increasing, decreasing, or constant? Now I'm going to take away the constant part because there is no constant interval. But how about increasing interval and how about the decreasing interval? Now, just to let you know here, by the way, before we totally answer this question here, we're going to put parentheses around everything. Okay, so if it goes up to like 2, we'll just say it goes up to 2 or whatever. Put parentheses around that. That's fine. It's a little weird how that works, but that's just the way we're just going to roll with it. So what about the increasing interval? What about increasing interval here for number 2? Be the increasing interval here for number 2. Negative infinity to 4. Negative 1 to 4. Okay. So so Sarana, you have two things kind of mixed together here. Okay. So I'm using negative 4 to 4 here. So what I see here is you guys are both using both x and y simultaneously. Okay. Why don't let's try it this way. For the intervals here, only use the x values. Only use the x values here. Okay. Let's put this as a thing here. All right. Only use the x values. Only use the x values for the intervals. Okay. Negative 3 to 1. Okay, so it's getting closer. Getting closer. Not quite there yet. Negative infinity to negative 1. Remember, this is for number 2 here, so negative infinity to negative 1, negative 3 to 1, okay, negative 4 to 2, okay. Lots of different answers here, okay. Let's take a look here at number 2, okay. So number 2 is this parabola here. Okay, so note, well, let's make a couple notes here. I think it's fair. We have lots of different answers here, kind of all over the place here. So let's look at each answer here. We'll break it down carefully, okay? I'm kind of glad I asked this question here, so that way we get this cleared up. Okay, so first and foremost here, again, as we know, interval goes from the lowest value to the highest value. All right, that's fair. Now, the one thing about this particular picture here is that we see that this arrow here is going down to minus infinity. So the first half here that we for this particular problem here, we have minus infinity as our guy here. Okay, so let's put that here. So minus infinity first and foremost. So minus infinity, and again with minus infinity, we always put a parenthesis next to minus infinity. Remember, we're just looking at the possible x values here. So although this looks like it dips down at minus 4, it doesn't necessarily stop at minus 4 because this arrow continues going down forever. Okay, so this actually reflects all x values below, say, minus 4, which is minus infinity. Now, since we're looking at the increasing one, let's see what value for x that it stops at. All right, and the value for x that it stops increasing is right here at minus 1. Okay, so minus 1 is where we stop here, and we're going to go ahead and put a parenthesis right next to that here in this instance. Okay. So this is our increasing interval here. Our increasing interval here is negative infinity to negative 1. So Stephen got that correct. Yes. Negative infinity to negative 1. Are there any questions about that so far? I want to be sure everybody's on the same page about, how I was able to find that. take a look at the x value that it stops there, E-Man. So E-Man, you need to look at the x value here. You're looking at the y value here of 4. I'm looking at the x value here where it stops increasing. That's here at x is equal to -1. That's where it reaches, say, the top of the hill here. Yeah, so Fritz, again, Fritz, you need to change your perspective here just a second, okay? You're looking at the y values. I want you to look at just the x values here, okay? So I don't want you to look at these y values here. I want you to look at the x values. At -1 is where it stops increasing, okay? That's the perspective I want you to look it over, all right? So I want to be sure that you're being very careful about that, all right? That's why, I get a whole host of answers here. I'm like, yeah, okay, let's go ahead and do that here. Um, why is it parentheses and not brackets for -1? That would mean that -1 would have to be included, and because a -1 can be, so the issue is that if we put brackets, excuse me, next to -1, that means that -1 would be included in that increasing interval, but then it wouldn't be included in the decreasing interval. So that would be a problem. We don't want to include it in either interval, actually. So we don't want it to be exclusive to one. We want it to not be exclusive to either of them. So we put parentheses around next to -1 as opposed to a bracket. So we're not actually including -1 here. And I know, to be fair, Blink, that's a very fair question. Okay, so I'm not discounting the question here, but I know it's weird the way that happens, but it just makes sure that -1 is not included in just one of the two intervals here that we'll describe. So it's kind of like its own deal because it's like a relative max or relative min. All right. Well, having said that, let's go to the other part here. We have the increasing interval here. What about the decreasing interval? So now that we have a good idea about how to express the increasing interval, what is the decreasing interval then, according to number 2? Okay. All right. That looks really good, right? So -1 to infinity. Yep. I know you just missed that negative there. So -1, and then that's going to go up to positive infinity. That's correct. Okay. So we start at -1. And this is going all the way up to positive infinity just for the x's here. And that's it. That's your decreasing interval there for this particular graph. Basics, let's get this basics down there. Steven, I think you just accidentally put negative infinity there. I think you meant positive infinity. At least that's what I think you meant. So I'm just gonna, okay. I'm gonna roll with that. I'm like, oh, okay. Like, bro. Like, that's cool, man. That's cool. Question: how do you get -1? Again, take a look at the x values here. Where does the decreasing interval start there, Joseph? All right, it starts here at x is equal to -1 here, according to the graph, and then goes all the way up to positive infinity. So again, you're what? So you need to change perspective here, Joseph. That's what I'm going to ask you to do. So I'm going to compel you. I need to compel you to change your perspective here. You're looking at the y values up here, my dude. I want you to look at the x values, this horizontal axis here. All right. So if you're looking at 4, you're looking at the wrong axis. You need to look at the x-axis here. All right. You're going to start at x is equal to -1, and then it keeps going up to positive infinity as a decreasing interval. Okay, so I just want you to think in terms of x values here. Doesn't matter what your y values are, because we're not talking about range. We're just talking about intervals here. If we switch perspectives here, it'll make a whole lot more sense here. Yeah. So I need you to change. I know it's tough. I know it's tough because you're like, oh man, nice number. I'm gonna go for that easy, nice number. I'd be like, cool, bro. You can absolutely do that. And I'd be like, oh, you know what? It's the wrong answer. That's not cool, bro. So yeah, I want to just be sure that you're looking at it through the right perspective there. All right. Let's try another though. I think another example is in order here, but we'll look at a slightly different portion here. Um, let's look at. I want to look at one more issue here. Let's take a look at that. Okay, let's look at number 13 here. Okay, so 13, you just have to be careful about how it's asking you the question, but in reality, it's not really super duper hard here. Okay, so 13. So you look where the -1, 4. Yes, that is correct, Danny. Always look at the x values only. Correct. I don't care about the y values, Danny. The 4 doesn't mean anything. It's just there, right? Ask the vertex of that parabola, great. But if it's asking us for the interval about where it's increasing, decreasing, x is the only thing I care about. So that's the perspective I want to look over because that's what it asked me to do. I said, fine. You want me to do it? Great. I don't have to worry about anything else. All right. So in this case here, it's kind of the same thing. So it says, okay, let's look at 13 here. You can see the graph here off to the left. Um, it says, letter A, it asks the numbers, if any, at which f has a relative maximum. Okay, so, and then what are these relative maxima? All right, so let's take a look here. Where do we have a relative maximum? First of all, what x values? Let's take a look at that. It's kind of a two-pronged question, but let's answer it in exactly as they state here. What x values do we find a relative maximum according to this graph we see here for number 13? What x values do we find a relative maximum? Yeah, right? 0, right? That's the only place we find a relative maximum, right? Say, hey, that's at the top of a hill. Sounds perfectly reasonable to me. All right, no problemo. Easy peasy. All right, good stuff. So far, so bueno. Now, the second part of the question is at what are these relative maxima? Okay, so they kind of ask this say, okay, well, what y value is what these relative maxima? So, or the point of this relative maxima is another way to put it. So what they may ask you is what is f of 0? I.e., what is the y value at x is equal to 0? So what would that be according to the graph? What's the y value at x is equal to 0? 4, right? That's correct. Okay, good. Now maybe you're not super comfortable about how it's written like this, but again, remember, f of x is the same thing as y, right? So f of 0 is equal to 4. Again, this just asks you, what is the y value at x is equal to 0? So let's put that in a text little thing. Again, to give you a friendly reminder here, right? So it says, this basically asks, what is the y value when x is equal to 0? That is exactly how you interpret that, okay? What is the y value when x is equal to 0? In this case, it happens to be 4, okay? So the answer here is 4. So essentially, you can read it this way as well. Again, we're more comfortable with this fashion here of 0, 4, right, as a point. But if we write it as f of 0 is equal to 4, that means the same exact thing as well. So wanted to point that out here is if you do see questions that look like that, then you'll know exactly what it's representing here in this instance, okay? So want to be sure that we get that cleared up, okay? Okay, let's take a look here at the other part. All right, let's look at letter B. All right, letter B says the numbers at which f has a relative minimum. All right, so what x values do we have a relative minimum here? Values do we have a relative minimum? Yeah. All right. Good beans. All right. So -3 and 3, 100% correct. Everybody. -3 and 3, easy peasy. All right. How about the second part here, which is what are these relative minima? We have f of 3 and f of -3. So what are these y? Let's start off with f of 3. Actually, they're both the same here, but f of 3, f of -3, what are those both equal to? 0. That's correct. Good, good. Wahaha. Evil. That's correct. Okay, good. So we do have the points here again. This will be 3 comma 0 minus 3 comma 0. You get the general. Same deal. All right. And there you go. Simple enough. Everybody's a winner. Nobody smells. It's great. All right. All right. Good stuff. All right. Nice work, everybody. All right. Okay. Any questions about that? Any questions? Right. Couple more. Discuss. Questions. Oh my goodness. Nope. Thank ya. All right. No. Okay. Good stuff. All right. Now, let's take a good look here at number 3. Number 3 talks about different types of functions. We can certainly discuss about that and what that's entailing and that's all about. Let's do it. Okay. All right. So what are even and odd functions? Okay. Even function here is basically if we plug in of minus x, if we plug in minus x, we get back the original function that we started with. An odd function basically is if you plug in minus x, you get the opposite of the original function that you started with. Okay. Now, I actually will put out one more note here. That is actually pretty important. Okay. It says many functions are neither even or odd. Okay. So one of the things we talk about numbers is like even numbers, odd numbers. Okay, fine. But functions are a little bit different because these are set definitions. So many functions don't fall underneath an even or an odd because again the definitions are very strict and rigid. All right. So in this case here, again, if it doesn't work out for either of them, that's certainly fine. It doesn't have to fall underneath an even function. It doesn't have to fall underneath an odd function necessarily. It doesn't have to be one of the two. It can be neither. Okay. So I do want to point that out here, so you're not like saying, oh, if it's not one, it has to be the other. The answer is no. That's not true. It just could be none of them. Like that's fine. All right. So let's do a couple of examples of this here. I'll show off some examples here. So let's do this one here. Um, f of x equals x squared minus 2. Okay. So if we have x squared minus 2, all we're going to do here is we're going to test for even and odd. So all we're going to do is we're going to do f of minus x. Okay. Now, just like we talked about with functions before in the last section, all we're going to be doing is plugging in this minus x in for this x in f of x. So we're going to have minus x in parentheses, quantity squared, minus 2. So what happens here is that minus x quantity squared, because it's in parentheses, effectively just negates the negative. And so we're just ending up with x squared minus 2. But x squared minus 2 is exactly the same function that we started off with. So, based on the definition that we have here, this would be an even function as a result. Okay, so we just ended up right back to where we started. Okay, after we plugged in minus x, that's what happened. Fine, that's it, we're done. Okay, next one here. Let's do the next one, the next example. These are going to be little quicker examples. So here we have x to the third. We'll go with plus 1. Okay. So if we go x to the third plus, actually, we'll just go x to the third. No, you know what? I got to do this. Yeah, let me change my mind here. Change my mind. Like, fine. I promise. All right, let's go x to the third minus 2x. Go with that. That's a little bit better. Then I'll go with the next one. All right. Trying to think of two things. All right. So in any case, um, let's go with again. What do we do to test even, odd, or neither? Again, you could plug in minus x. We're just going to plug in minus x into this equation. Minus x to the third power minus 2 times minus x. So again, minus x to the third power here is equal to minus x to the third. Minus 2 times minus x is plus 2x. And again, if you did this out here, you would find out that this guy here is the opposite of our original function. Again, if you want to test that here, you can do minus x to the third minus 2x. And then again, distributing the negative here to both of these guys, that's going to be minus x to the third plus 2x, which is what we got here from. Okay, so just to justify here what we got. All right, so of course, this says here this is an odd function as a result. Again, pretty rigid about how it works. It's like, fine. All right, no problem. Okay. All right, let's do one more example here. So f of x here is x, let's say x squared minus 7x plus 3. Okay, and let's say we want to test for even, odd, or neither. Nothing too fancy about this one here. It is what it is. And you're like, all right, cool, let's do it. And you're like, okay, let's try plugging in negative x here again. Rinse and repeat the same process here. So negative x, quantity squared, minus 7x, oops, sorry. I meant the minus x should go there. My fault. My bad, my bad. Okay, so negative x quantity squared is positive x squared. No problem. Negative 7 times negative x is plus 7x. And then we have the plus 3. Now, let's take a look at this particular function. This particular function is not the same as our original function, so it can't be even. It's close, but it's not quite the same because we have minus 7x here and we have plus 7x here. So it can't be even. It can't be odd because, again, if we did the opposite of this original function, we would have minus x squared plus 7x minus 3, which is clearly not what we have, what we don't have here. So in this case here, because it's, again, doesn't follow either of the definitions, this is going to be neither. Okay, so this is a clear example of where a function can be neither even or odd. All right, so many things follow this pattern here. So there you go. All right. Questions? Questions about that? Hopefully that is not so harsh. Okay. Okay, fine. Okay, so why would that be neither again? This would be neither because it did not come out to be either the original function, f of x. So this didn't come out to be the original function here. And this is not the opposite of the function here, which is negative f of x. So negative f of x here would be the opposite of this. So again, that would be, in this case here, Like if you tried negative f of x, for example, that'd be minus x squared minus 7x plus 3. And if you distribute the negative here, that'd be minus x squared plus 7x minus 3. So this final result that we got here is not the same as if it was the opposite either. So it fell into a category where it didn't satisfy either of the definitions, Joseph. And so that's why it's neither here in this particular case. Like I said before, many functions here actually fall underneath the neither case because this usually happens. So how did I get the answer to the question before this? Are you talking this one here, x to the third minus 2x? E-man? Oh, okay. So for this one here, I replaced minus x. Minus x to the third is minus x to the third. Again, that was again a negative times a negative times a negative. So one of the things that you'll have to recognize here is that minus x to the third here is negative x times negative x times negative x. Okay? So that equals negative x to the third here. Minus 2 times negative x, that's going to be plus 2x. That one's pretty easy to see. Now, if you want to find out that was odd here, now this is what I did here to kind of justify how it's odd. I took it to say, okay, what if we did the opposite of the original equation? So minus x to the third minus 2x. Well, that's equal to minus x to the third plus 2x if we took the opposite there. So what we got as a result here is we got the same exact thing as if we took the opposite of the original function. All right, hence why we get minus f to the f of x, which would indicate that it would be indeed an odd function here in this case. So if you say, hey, you know what, I'm not sure if it's going to, even function is pretty easy because you just have to look at the original function. Maybe you're a little confused about odd. You're like, okay, let's find out what the opposite is, and then compare, and you're like, okay, is it the same as the opposite that I found it doing the other way? And you're like, oh, it is. Okay, now I know it's odd. All right, fair enough. If it's not, you're like, okay, maybe it's not odd then. So any other questions before I move forward? Any other questions? Actually, do I have time for that as a question? I might have. Hey, actually, I may have time for that. So yeah, I do have time for that. All right, good stuff. Okay. All right, so we're almost done here with section 2.2, but it'll be we're gonna do this. This will be the last question we'll do here for today, which is number 4, and then we'll continue on here with number 5 from the last question, which is the last question from 2.2 for next time for tomorrow, which shouldn't take us too much time. But let's go ahead and do number 4 here because I do want to at least show that off here for today. All right. Blink says hydrate. Fair enough. Thank you, Blink. Thank you. All right. Just like hydrate too. Fair. All right. Thank you. All right. All right. So let's look at number 4 here. Number 4 says, how do we evaluate and graph a piecewise function? So how do we evaluate and graph a piecewise function? So first of all, let's talk about what a piecewise function is. A piecewise function is a function broken up into pieces. So what we're going to do here is, as it says here, we're going to make an XY chart here for each piece. Then we'll talk about the last two things that are listed here about open circles, closed circles, okay? But I have a little bit of a method to show you what points are included and what points are not included. But in order to show you this here, we need a practical example to kind of put it together. So let's go ahead and take a look. All right. So a piecewise function is going to look something akin to this. Let's look at I kind of like this one. So 0 if x less than 3 x yeah x plus 1. Get this down here. Okay, so here is our piecewise function. Notice in this case, we're going to have 3 pieces of the graph here. Okay, now this is broken up 3 ways. Now, the important part here to think about is the thing that we want to focus on here to make this less overwhelming is basically looking at the restrictions that we have here off to the right. So, for example, here this says f of x is equal to 0 if x is strictly less than minus 3. Okay, now we want to specifically look at this restriction here because, again, certain values are not valid for this first piece of the graph because we have to follow the rules. So let's say we're doing an XY chart for each piece. So this time here, I'm going to make this a bit bigger here because what we're going to do here is we're going to take this apart here one piece at a time. I'm going to make an XY chart here for each individual piece of this graph. So let's look at an XY chart here for the first piece, which says f of x is equal to 0 if x is less than minus 3. Okay? All right. Now, first things first, I'm going to need your help for this one here. Let's think of the restriction here. The restriction here is x is less than minus 3, right? What values here are less than minus 3? I need to pick values here for x, but I have to follow the restriction. What values are, pick a value that's less than minus 3. Let's pick a value. Okay, fair enough. So, La Serena, you're correct. Okay, minus 4, minus 5, minus 6 seems fair, right? Fair. Absolutely fair. What values for y am I going to get for minus 4, minus 5, minus 6? What value for y do we get here for minus 4, minus 5, minus 6? What does it say? What does it say here in this case? It says, is that what it says? I don't think so. If I plug in x is equal to minus 4, what do I get back? I get 0, right? Because everything I plug in, right, doesn't matter. I plug in minus 4, I get 0. I plug in minus 5, I get 0. I plug in minus 6, I get 0. Okay, so that's what I'm going to put in here. 0 and 0 and 0. Right? Doesn't matter what number I plug in. Automatically, things become 0. And that's just the way it works. Okay, that's the way it is going to be. Okay, fair enough. Now, those are 3 valid points, 100%. Now, I'm going to include one more point here. Now, this is the important part. I do need to include one more point here. And you're probably saying, you do? Like, yeah, I kind of do. Because I do need to know where to stop for this piece of the graph. And so the last point I need to put in here is I need to put in minus 3. You're probably saying, whoa, 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 time out, time out, time out. Hold up a second. Minus 3 is not included in the is not in that piece of the graph. I'll be like, yes, but it does tell me where I need to stop. I said it's true. Minus 3 is where I need to stop. We can't forget about the numbers here between minus 4 and minus 3. That still is applicable as part of the restriction. You know, minus 3.1, for example, is still valid. That's still less than minus 3, okay, for example. If we plug in minus 3, we get 0. But what we're going to do here specifically is, because we have x is less than minus 3, we're going to draw a little box around this because it's a special point, unlike the first 3. The other first 3 here are just like, hey, they're definitely part of the graph. So we're going to definitely put those. Just need to know where to stop. I'm going to put a little box around this. And because we have a strictly less than here, we're also going to put here, in this instance, we're going to put that this is not included. Okay. Okay, so this is not included because it's strictly less than here in this case. So if it says as 0, if x is less than minus 12, the stop point would be minus 12. Correct. That's correct, Danny. Absolutely right. That is where we're stopping. And then we're going to read off the inequalities there. Again, either whether it's included or not included. That's exactly the right idea. Okay, let's look at the next one here. Let's do the next piece here. Half of x is equal to negative x if we have negative 3, and between negative 3 and 0 here. So we'll make an xy chart for this. And this is our second piece. Okay, again, we're now going to go ahead and put in our points here. We're going to need to know where to start from. Again, we know where to start because x is bigger than or equal to minus 3. So minus 3 goes here. Now, if we plug in minus 3 into this piece of the graph, then we get minus 3, which is going to be positive 3. And I'm going to go, I know I'm running out of time here, so it's going to go over this a little bit quickly. However, again, this is a special point here because we need to know where to start. Now, minus 3 comma 3, this is going to be included here. This point here will be included. Again, because we have the strictly bigger than or equal to sign here next to minus 3, we want that point to be included here. Now you can pick various other points here that is between minus 3 and 0. Again, you could pick minus 2. Minus 2, we get 2. Like minus 1, we get 1. Fair. And then finally, we need to know where to stop for the second piece of the graph. And to stop for the second piece of the graph, we need 0. If we plug in 0, well, still going to get 0. However, once again, looking at the inequality here, because this is our special point, and this tells us where to stop, because our inequality here is strictly less than here in this case, then this point here is going to be not included as part of the graph, as part of this portion of the graph. So, be not included. Right? Okay. Any questions so far, by the way? I hope everybody is kind of understanding about where this is going. It's going to take just a few more minutes of your time. I apologize. No? Okay. No. Okay. Now the last piece here is going to be x squared minus 1. This is if x is bigger than or equal to 0. Okay. Good. All right. So we're going to make another xy chart here. Again, as you can clearly tell, we're going to start at 0 here. You plug in 0, you get minus 1. Now again, let me ask a quick question here. Is 0 comma minus 1, is that included or not included? Would that be included or not included? Let's at least answer that question. Would this point here be included or not included? Okay. The answer is definitely true. It is included because we have bigger than or equal to 0 here for this particular piece. So we have included. Good, good. Okay. We could try other points here. You could try 1 we get 0. 2, we get 3. I guess that's as far as I'll go for that one. Really, it's not too hard to do. Okay. So, but that's the most important piece here is 0 comma minus 1 is included because of the bigger than or equal to here in this instance. So again, I know you're a little confused there, E-Man. It just depends on the inequality that you're given there. So that's why I'm kind of circling it just to be sure. Be like, hey, you have you make sure you're not guessing here. You're saying, okay, how do I know this included? Look at that inequality, right? And just check that out and says, okay, if I see a bigger than or equal to, less than or equal to, I know it's going to be included. If that's strictly less than, strictly bigger than, I know it's not included. Okay, I want to be sure that that's clear for you there. Okay, now we're going to go ahead and put it on a graph. Let's put this all on a graph. Let's knock this out of the park here. All right, so 1, 2, 3, 4, 5, 6. All right. So let's look at this first part here, this first graph. We have minus 6 comma 0. Put that down. Minus 5 comma 0, minus 4 comma 0. Now, minus 3 comma 0 is not included. Now, this is kind of, let me go back here to the notes here one more time. We're going to use a closed circle if the points are included, and an open circle if the points are not included. That's why I have these two little guys here. That way, give ourselves a reminder here. It says, okay, if we put included next to that, closed circle at that point. If we put not included there, we're going to put an open circle at that point. Okay, that's the point. That's the idea about why I put that there for this particular part. So if I'm looking at this, put this as a side. If I'm looking what we have here, all right, just following that first part there, I'm going to go ahead and put an open circle here at minus 3 comma 0. So there's an open circle there at minus 3 comma 0. And this graph, this piece of the graph here, just in red, just going to go off to the left, just like so. Okay, so that is the first piece of the graph, just like so. Second piece of the graph here, we start off at minus 3, and we say minus 3 comma 3 is included here. So let's go ahead and put this down here. So that's going to be a closed circle there at minus 3 comma 3 because that point is included in the second piece of the graph. We want to go ahead and do minus 2 comma 2. That's kind of a gimme. So and it'll be closer because that's definitely included. Minus 1 comma 1 here. However, again, 0 comma 0 is not included. We're going to put a open circle here at 0 comma 0, and that's where that piece of the graph is going to stop. So here in orange, I'm going to stop right there. There's the second piece of the graph, just like so. Finally, let's do the third piece of the graph here. We have 0 comma minus 1. I'll put that in green. So 0 comma minus 1, that is a piece that is included here. So we're going to put a closed circle here at 0 comma minus 1. And we have 1 comma 0, 2 comma 3. So those parts are not too hard. Just have to plot those points. So if we connect this, and this goes up forever, because and so here we go. We have the third piece of the graph, just like so. And there we go. We have effectively now put together a piecewise function. Okay. Any questions about that? I apologize for running a little bit over time here, but I wanted to show off this example for you, so you get a clear-cut look about how to tackle these. So. Yeah, I just want to be sure we cover our bases. Blink, you can right after this stream ends, you can immediately look at the replay here. It's uploaded immediately here to Twitch underneath the videos. So once my stream is over, it'll automatically be up here on Twitch right after I'm done. So it stays up here on Twitch for 14 days. I'll then upload it to YouTube after 48 hours. So there you go. Did I graph 2 comma 3? Yes, that is this point right here. That's 2 comma 3 right there, George. Yeah, so if you need to rewatch it, it's going to be up here right away. You don't even have to wait 24 hours. Where do you go again for the stream on Twitch? Well, you just come back to this channel page, right? So to answer your question here, you come back to this channel page right after I'm done with my stream here today, and you'll click on the video. There'll be a set of tabs on the top underneath my channel intro, whatever the heck you want to call it here. Um, and it'll say videos. If you click on videos, it'll have our videos that we had here, that I have on for the past 14 days. So obviously that'll be in these first 3 classes. So just to let you know how that'll go. Okay. So right after I'm done here, that's how it'll go. That's fine. No, I'm here to make things easy. So that's why Twitch is really super handy. So it's like you don't have to worry about the replays here. I then upload it to YouTube after 24, 48 hours, so I have it in archives. So, but there's multiple ways you can get access to it. All right. I apologize for going a little bit overtime here. Oh, that's our Discord page here. You can contact me through the Discord, of course. I wanted to go to this. There we go. All right. I want to thank everybody here for coming on the stream. Thank you for spending a little bit extra time with me for this last example. I so appreciate it very much here. All of you guys are wonderful. You guys are great. I love you all. Thank you so very much here for today. We're going to come back here noontime tomorrow and continue moving forward here in Chapter 2. We're not quite done with the last section here at Section 2.2, but we'll finish off Section 2.2, move on to 2.3, and maybe a little bit of 2.4 here for tomorrow. All right, thank you again so very much. I want to thank Formal Monkey here for gifting 5 subs. That's quite amazing. Some of you got some subs, so I appreciate that. All right, thank you, everybody. And as always, everybody, stay safe, stay healthy, and most importantly, everybody, stay sane. All right, have yourself a wonderful day, and we will see you here tomorrow. All right, take care, everybody. Have a great one. We'll see you later. All right. Contact me on Discord or email if you need help this afternoon for whatever. All right. All right. Take care, everybody. See you later. Bye.